number times x to some power. And again, that power can't be 0 because x to the 0 is just 1. When 1 times, then it's not a power function anymore. It's a constant function. So these are power functions. We're going to learn all of them. So a power function is also a type of monomial function. Monomials meaning single term. And so we want to draw a little sketch of each of these. The constant function would be f of x equals some constant c, meaning something like f of x equals 3. Well, this is just a constant 3 where the y value is 3 all the time. It's just a horizontal line, right? So that's the constant function. It's just whatever that constant value is. It's just that horizontal line. That's a constant function. Linear function would be f of x equals x, right? Linear function. That line, this particular one, is our 45-degree line right there. Yeah, going right through the origin. It's got a slope of up 1 over 1. That is our straight-up linear function. Our quadratic function is f of x equals x squared. The very most basic quadratic function. What shape is that quadratic? Parabola, sure. And it goes through 0, 0. It's this gorgeous little parabola going through 0, 0. So all of these are monomial functions because they have a single term without all the bunch of extra stuff, okay? We have the cubic function, f of x equals x to the 3rd power. What does x to the 3rd power look like? It's like it's a stretchy S thingy. So it goes and it's got this nice little graceful curve. I think there's like a good water slide over at, what is the water slide place over in Boynton? Avalanche Bay, yeah. So anyway, that's the one where you get in the tube. Yeah, it drops down. Yeah. That would be super scary. Yeah, I would. That would. Yeah. All right. Quartic is x to the 4th power. What does x to the 4th power look like? Wait, do it again? So, okay.
Above that goes to 0.
So, if it had extra terms, it can look something like this, okay? If it has extra terms. But the plain Jane, x to the 4th, we can, if we are unsure, we can check x to the 4th, there it is. It actually looks like the quadratic, except it's sort of flatter on the bottom. And so I'll show you the quadratic so you can compare. So in red is going to be the quadratic. So you can see it's growing faster because we're taking values and raising them to the 4th power. So if you plug in a 2, here if you plug in a 2 squared gives you 4. But here, if you plug in a 2 for x, what do you get? 16. All right, so when you plug in a 2, this is raising it to the 4th power. It's getting taller quicker, all right? And so it's sort of, when it's just a plain Jane function like this, it just looks a little flatter on the bottom because those little fractions get littler, all right? But numbers over 1 get taller quicker, okay? So anyway, there's our quintic, which should be what? X to the 5th. It does get taller, but it's the same general shape as the cubic. But again, because it's to a power of 5, it's going to grow faster. So it looks skinnier, but really it's just growing quicker, getting taller quicker. Boys, do I have to blank your screens? Are you sure? Because I'm feeling like I do, and I have to do that with the 8th graders, and I just feel like you should be more mature than that. Okay. All right. So you'll notice here what's happening, and we can imagine here if I had x squared and x to the 4th, what's x to the 6th going to do? It gets taller still, right? But it's the same general shape.
So it's like even
Yes, evens and odds. Very good. So even monomials, their arms always match. The arrows always go together. They're even, all right? That's even symmetry, okay? But if it's got the odd powers, the arms are always odd. One is low and one is high, okay? And so this is important to think about because it lends itself to symmetry and in behavior of many, many, many different types of functions. So if the function has an even power, then it is symmetric about the y-axis. And you can see that in the pictures. They are very even in nature, meaning if I take this point, it gets reflected across the y-axis. So we have symmetry on both sides of the y-axis. It's a mirror reflection across that y-axis. And then if the function has an odd power, then it is symmetric about the origin. Odd origin. So it has that same sort of symmetry. I'm not going to do it as that, but like here we might have the point 2, 8, and it gets reflected through the origin and out the other side at -2, -8. Exactly. And that's that odd symmetry. Now, this is only true when we are looking at monomial functions. The minute I shift this left 4, it's no longer symmetric about the y-axis, right? So these are just straight up very pure monomial functions. We can also tell a lot about the end behavior, and when we say end behavior, we're wondering what the arrows are doing. So we have only 4 different kinds of end behavior. I don't remember this stuff. I know the picture of the graph in my head, right? And so if I have, for example, our favorite quadratic here, y equals x squared, I can see that the arrows are both pointing up to positive infinity. So the end behavior, now we've already done this, so we're going to refresh our brains here. The end behavior discusses what happens as x goes from negative infinity and as x goes to positive infinity. So every single one, when we talk about end behavior, they all start the same way. I'm going to go ahead, take a second, and just write it in so that we can just fill in the blanks. As x approaches negative infinity, as x approaches positive infinity, as x approaches negative infinity, oops, that's -100, not negative. Okay. And as x approaches positive infinity. So we always want to know what happens to the y values when we look on the left side and the right side of the graph. So on this first quadratic here, as x approaches negative infinity, well, the x-axis is here. Negative infinity is over here on the left-hand side of the graph, really far down. What's happening to our y values? They're going up and they're going out. They're going up. The y approaches positive infinity. Now, I probably shouldn't use y. That's the shortcut. I probably should use f of x because that's the notation they gave us. But it means the same thing. F of x is just fancy. Fancy for y. As x goes to positive infinity, so that's the right side of the graph. Over here on the right side where x's are very, very large, what does the y value do? Yeah, it's going up to positive infinity. So f of x is going to positive infinity. All right, what happens when I pop a negative in front of my x squared? What does it do to the graph? It flips it upside down. So now, what are my function values going to do now? Yeah, well, so now as I move, Yeah, they're both going down here, downward to negative infinity. So the left side goes to negative infinity, and the right side of the graph also goes to negative infinity. Now, odd functions, here we have our cubic, and as x approaches negative infinity, so that's the left side of our graph here. So on the left side of our graph, what's our function doing? Negative infinity. So f of x is growing downward to negative infinity. So it's really like, what's the left arrow doing? What's the right arrow doing? So over here, this is saying, hey, as x approaches positive infinity, that's to the right side. So what's our right arrow doing? Positive infinity, yep. And then, of course, if we put a negative in front of that cubic, what was here, low to high, flips. And now it's going high to low. It's a decreasing function. It's going downhill from left to right, okay? And downhill. So now, again, as x approaches negative infinity, so that's the left side, what's our function doing? Going up. So f of x is going to positive infinity. And as we go to the right, what's our function doing? Negative infinity, going down to negative infinity. All right, and behavior, easy. Symmetry, easy. All right, we good? Positive, negative.
Oh yeah, I just flipped them. I put them.
So always you got, this is like the left side and then the right side. So left arrow, right arrow. Yeah. Okay. So what happens, now the nice thing is you guys have calculators. You are absolutely allowed to use your calculators. So we're going to do a couple. I'm just going to show you a few of these, what we want to see here. So I'm just going to look at number 1. First of all, 3x to the 6th, what's the general shape of this thing? Eyes up. It's like a parabola shape, yes, it's even, okay, and it's really tall, all right? That 3 makes it even taller still. I know it goes through 0, 0, but we can graph this if we really want to look. Yeah, so we have 3x to the 6th power. And we can graph it and look at it. You are absolutely right. If you plug in a 1, we get the ordered pair 1, 3. And if you plug in a negative 1, you also get the ordered pair negative 1, 3. So it has symmetry. You could look at the table if you wanted to and see that we have 1, 3 and we have negative 1, 3 on there. But look how big those numbers get super fast. You plug in a 6 and you're already at 139,000. Okay? So this function grows super, super duper quickly. So we have our basic shape here. Let's talk about domain. What is domain? Yeah, domain is how far left and how far right the graph goes. So what is the domain? Infinite, yeah. I'm just going to put the big all real numbers here, but negative infinity to positive infinity would work with parentheses. What is the range here?
0 to positive.
Yeah, low to high. So the lowest value is 0, and the highest value is infinite. Can I just say y values greater than or equal to 0? I could absolutely say that. You could do, in this case, you could also do bracket 0 to infinity. Either one of these answers is totally fine. But y values greater than or equal to 0 means the same thing. What's the x-intercept? 0, 0. What's the y-intercept? 0, 0, the origin. I hate all these questions. I don't care about these really most of the time, but we'll just do one. We're going to do one, okay? What is the increasing interval?
Infinity to infinity, and like
So increasing means going uphill. So this whole arm here is increasing, going uphill. Where does it start going uphill? At 0, yeah. So the increasing interval starts at 0, and it continues increasing for all the x values, so all the way to infinity. And we don't usually, we're just going to go with parentheses on that interval. So every book defines it differently, and I'm going to go by the calculus answer, and that they will never really actually grade this. They will never grade those endpoints. So we're going to keep it simple and just keep them open. Yeah. But yes, you are right. It is increasing from 0 onward. Technically, yes. But yes, so the decreasing interval is going downhill. That's the other side. So from negative infinity all the way to 0, we are decreasing. And the symmetry, yes, it has y-axis symmetry. Very good. Discontinuities, none, very good. And the end behavior, as x goes from negative infinity, what does our function do?
Positive infinity.
Yep. And then as x goes to positive infinity, what does our function do? Still positive infinity, up both times. Perfect. Okie dokie. Is that pretty good? Yeah, you good with that?
Yeah.
That's what I thought. Let's.
Have to put the positive sign?
You do not.
Okay.
I like to because it's one of those invisible math things that as a teacher I never want anything invisible. All right, turn the page. So, in addition to power functions where the power is an integer, a positive integer, we could also have powers that are negative integers. And so we want to remember what happens when we have a negative power. X to the negative 1, what does it mean?
I don't know.
1/2.
Is one over x is right, yeah. So if you, like, I know, Brody, what you're thinking of is, like, you're thinking, like, 2 to the negative 1. Yeah, 2 to the negative 1 is 1 over 2, and 4 to the negative 1 is 1 over 4, okay? And so x to the negative 1 is 1 over x, okay? It creates a fraction. It's a reciprocal. And so 1 over x is called the reciprocal function, which, again, we've already seen before. So this is our reciprocal function. And it's important that we remember that because this is really a fraction, we always have a denominator, and denominators always create domain issues for us. The denominator can never equal 0. So that means in this case, x cannot equal 0. Anytime you have a fraction, we create problems with domain. We create things that are undefined. And so power functions with negative exponents are undefined when x equals 0. And therefore, they will have discontinuities. So here is our function. Because that x is not allowed to be 0, we create this infinite discontinuity. That is that vertical asymptote right there. This function also has this horizontal asymptote, which we're going to really officially learn this chapter, okay? We'll talk more about that. So once again here, we're going to look and see what is going on with these kinds of functions. This one is very interesting. I love this function. It's like a volcano. It is kind of like a volcano. Let's look at it. So again, when in doubt, graph it out. We have 4x to the negative 2 power. When in doubt, graph it out. It is the volcano function. It's very cool. So what's happening here, this is the stuff I absolutely love about functions. We're taking this reciprocal function and essentially squaring it. And if you take a number like -4 and you square it, what happens? Well, what is -4 quantity squared? Positive 16. So what it's doing is essentially taking this portion that is negative, it's in the negative y values, and it's flipping them up, making them positive, which is really kind of cool. So this is our 4x to the -2 function. I'm going to look at the table just so we can see what some points are here. We have -1, 4, and 1, 4. So we do have symmetry. And so it's just sort of like a volcano. That is a great description. Again, it has symmetry because of the even power. So there is definitely symmetry with respect to the y-axis. Does it have a discontinuity? Yeah, it does. It still has this, because again, it's 4 over x squared. That x squared is not allowed to equal 0. So it has this, again, this sort of undefined thing right there. X equals 0 is an infinite discontinuity. And again, it just comes from that domain, the denominator. Denominator, domain, denominator, domain. What is the domain of this function? So almost. You have to stop at 0, yeah. You know what, for the domain of this, I'm just going to say x cannot equal 0. X cannot equal 0. Is everything else okay? Everything else works, but x is not allowed to be 0. And the reason it's not allowed to be 0 is because if I do 4 divided by 0 squared, I get undefined. You can't divide by 0. That's a big fat error. All right? So that is why x cannot be 0. If you plug it in, it shoots you an error message. Okay, what is the range? What's the lowest y value? It gets so close to 0, so we're not going to include 0, but it gets infinitely close to 0. And then it's everything above that. So 0 to infinity, not including the 0, would be the range. You could say y is just greater than 0 if you want to write it that way as well. Either suffices. Do we have x-intercepts and y-intercepts?
No.
None, yeah. What's the increasing interval? Yeah, the left portion here is increasing, going uphill. So over what x values does that occur? Negative infinity
0.
to 0. Good. Negative infinity to 0, but we don't want to include the 0 because we can't include the 0. All right? And what's the decreasing interval?
0.
Yeah, 0 to positive infinity. This side is the very fun slide. Going downhill. That is a fun slide right there.
I don't know, it feels like you could stop.
Have you done that? Like the cross your arms, cross your legs, like water slides?
No, I can't, I get nice.
I've only done it once. It was a long time ago. Okay. Okay. In behavior, this is an interesting one. All right, as x approaches negative infinity and as x approaches positive infinity. So looking at our graph here, as x approaches negative infinity, so as we are moving towards negative infinity, what is our y value doing? It's decreasing, getting close to 0, yes. The function is approaching 0. All right, we are not going to infinity on a function like this. We are getting infinitely close, closer and closer and closer and closer and closer to 0. All right, that's very interesting. And then as x approaches positive infinity, so as we're out here on the right-hand side, what is our graph doing? Getting ever closer to 0 again, getting lower and lower and lower to closer to 0. Excellent, excellent. Let's talk briefly about number 2 here. Is this an even or odd function? It's an odd function because it's got an odd power. So it's very similar to our odd function here, which is taking up quadrants 1 and 3. But this one has a negative in front of it. What's that negative going to do to our... It flips them, yeah. So what originally would have been little L shapes in quadrants 1 and 3 are being flipped, and now they take up 2 and 4. All right, so that negative, it just flip-flops everything. So again, double check if you want to. We can type it in. We can see negative x to the negative 5th power. And it's a very sharp L shape. All right, but they are now taking up quadrants 2 and 4. So very cool. Again, we've got discontinuities there. And all of this is just stuff that, you know, I sort of want you to think about. What's number 4 going to look like? So as I'll take Colt's word, this is like a volcano graph, but it's got a negative in front. So the volcano went like, yes, upside down, yeah. So, all right, so negative 2
Also, it's like the Grand Canyon.
x to the negative 4th power. So yeah, so this is what I love doing. I love just like, hey, let's imagine what this is supposed to look like, and then, hey, there it is. So yes, we are a big cavern here. Mariana Trench. There we go. Okay, so, all right, do you have questions for me, or you think you got it?
No, I think
All right, you've got calculators, you've got, all right, I think that's all we got to do today.